bit of information about the eAccelerator. The accelerator is the module that we have coupled to the out-of-order execution risc-v processor that Nahir just talked about. And here's where we accelerate the cool applications, right? So what we are focusing, so there's this description of the task, but so our first question was, how are we integrating this together with the processor, or is it working as a co-processor? And we went for the second one. And the diagram that you can see in the slide is kind of showing the high-level modules for this accelerator. So core of the accelerator is a vector processing unit, and then we do have interesting features in the functional units. And by interesting, I mean the support of multiple formats to do our calculations. This is particularly interesting for machine learning applications, as you know, as well as other applications, but machine learning do exploit all of these features. And the focus in this project was for low precision floating point operations. Why? Because we are kind of looking at, so the processor is focused for HPC, and therefore training is one of the important things there. And we wanted to offer something that has the capability of do very efficient training with very low precision floating points. So we do go low to 8-bit floating point operations. So this then is integrated in a way that we'll show in the next slides to perform AI acceleration. There is also an effort on doing targeting bioinformatics applications with some acceleration and special instructions. And then obviously we have effort on the interface to the core, because as I said before, this is a coprocessor. So, and sorry, just really important for us, and maybe our slides are not very fancy because we are working day and night to achieve this goal, which is having the first version integrated and UVM verified. Okay, so this is, we can claim that we achieved this already. So that's really good. Now, in terms of the vector processing unit, I told you it's like the core thing of our accelerator. So this is a BSc led effort. And here, I'm not going to read you all this text, but just to give you the highlights. So we are currently with 4 vector lanes, plan to have 8 vector lanes in the second tape out. And we have maximum vector length of 32 to 256 elements, 64 bits, maximum size of the vector 64 bits, and we have fused, multiply, accumulate, and again, you know where this is going, right? I talked to you about the floating point. There is also something that I didn't highlight, but we do have also multiple formats for integer operations, and these go as low as 1-bit integer, I would say. This is in the plan. And then we do have the direct access. I mean, again, it's obvious that when you have an accelerator, the important thing is to feed the accelerator. We saw this in other presentations too. So we do have a direct access to the L2, which can also work as a scratch pad. And we are going to exploit that feature. And there is a limited out-of-order capability for the vector operations in memory. So the other important module of the accelerator is obviously the interface with the scalar core. As we are in a co-processor, we need to communicate with the scalar core. Scalar core sends us the instructions to execute. One of the important things you can see there in the second bullet is that we do operate asynchronously. So our coprocessor is operating while the processor is also operating. So we do need to communicate when we are done. And that's what it's saying there. We share the common data bus and support for the CSR instructions and so on. Another thing that I would like just to point out is, because we are dealing with an out-of-order execution scalar core, in some cases, as you know, instructions need to be rolled back, and therefore there is a special signal going to the coprocessor to act upon that. So we need to recover from that. Then the other important part are the functional units. I already told you this, right? I mean, it's one of the key things for us in here in the accelerator is the flexibility that we can offer in terms of support of different formats. So in here you can see that we did encapsulate this. This is our way to see it. So we do have you can call it a framework. When you're too close to the board, this is what happens. But we do have a framework where from outside abstractly you see it as a functional unit, and inside you have different implementations for these functional units. And we do support the risc-v instruction set for this. So they are incorporated into the vector unit. So they can be calling, the vector unit can be calling these functional units. They do support the rounding IEEE modes. We do support IEEE on the 64, 32-bit floating point units. The 16-bit floating point is implementing the BF16, so for targeted for machine learning, as I said before. And then we have the 8-bit FPUs, which actually are supporting two formats, the 143 and 152. This depends on the mantis and the exponent sizes that we are trying to do. The other important thing that you see here in the horizontal lanes here, passing these arrows from one unit to the other one, is if you are aware of what is going on in machine learning operations, or any operation, even if it's a multiply operation, when you are multiplying or doing some operations in low bit format, they will end up with higher bits. So therefore, we have widening capabilities of for the instructions. So an 8-bit operation can be scaled up to 16-bit and then to the 32-bit operation. That's what we are doing here. Yeah. In addition to the floating point, we have also the integer that I told you. And this is originally the 64, 32, 16, 8, but we are going to implement also 4 to 1, as it said there. And to wrap this up, so the other module is the AI accelerator. So the idea here is to support, as you know, the core operation, which is the general matrix multiplication that we require for the machine learning codes. An efficient implementation for matrix multiplication, as you know, is a systolic array. And this is because we use the data flow to avoid temporary results. So it would be implemented well in the vector unit, but a systolic array is more efficient. So we are exploring that. The cool thing here, I can say, happened as it's like when you read these experiments about how rubber was invented by accident. So by accident, we were not having resources to do our systolic array. Thank you. And that gave us the opportunity to do something more cool, which is let's reuse the units and offer a systolic array functionality out of the units that are there in the vector processing unit, original vector processing. So what we do is we reorganize the flow of the data so that we can have the functionality of the systolic array, but reusing the same unit. So we don't need to have a systolic array on the side of the vector unit. And that is a really nice thing. And so it's what we call there as a hybrid architecture, low area overhead. So we can get the efficiency and we can get the functionality that we are expecting for these applications. So we are really excited about testing this in the real world. We do support the extension, ISA extension for the risc-v for doing the matrix multiplication in this case. And what we are showing here is a diagram of one of the lanes that we steal the resources from the vector unit to do our calculations, in this case, with the implementation of the BF16 operations and the accumulations over there. So I think that is it for the accelerator.